In proposition 28, what we're going to show is that if we have a straight line which cuts through two other straight lines, and if it's true that the exterior angle is equal to the interior and opposite angle over here, then we may conclude that these two lines are parallel. And the second part is that if these two interior angles are together two right angles, then we may also infer that these two lines are parallel. So two parts to this proposition. So let's check out the text. If a straight line falling on two straight lines make the exterior angle equal to the interior and opposite angle on the same side, or the interior angles on the same side equal to two right angles, the straight lines will be parallel to one another. And let's check out the setup. We'll let the straight line EF, that's going to be EF, falling on the two straight lines AB and CD. Let's label everything here. That's going to be EF, B, and CD. Make the exterior angle EGB, and what is G? G is going to be this intersection over here. That's going to be G, and also H, as we'll see in a second, that's going to be over here. Make the exterior angle EGB equal to the interior and opposite angle GHD, which is over here. As you can see, it's interior because it's over here, and it's opposite. If these two are equal, or this is going to be the second part of the proposition, and we'll come back to this in a second, or the interior angles on the same side, namely BGH and GHD equal to two right angles, I say that AB is parallel to CD. So we're going to take the first one. For since the angle EGB is equal to the angle GHD, as we've diagrammed here, while the angle EGB is equal to the angle AGH, and why does he infer that? That's equal to the angle AGH. Well, these two angles are vertical angles, and vertical angles are equal, as we've proved in proposition 15. The angle AGH is also equal to the angle GHD, and they are alternate. So notice what's going on here is we have the angle EGB, which is the same as AGH. And notice now we have alternate angles, AGH and GHD. And we may conclude by the previous proposition, number 27, that when the alternate angles are equal, these two lines are going to be parallel. And let's think about the second part of the proposition. Again, since the angles BGH, we have the angle BGH, and also GHD, what's going to be true about these two angles? What's going to be true is that together they are going to be two right angles. As he says, since the angles BGH and GHD are equal to two right angles, and the angles AGH and BGH, so let's mark what he's talking about here. He's saying that AGH and BGH are equal to two right angles. Why are they equal to two right angles? Well, we have the straight line over here, and the adjacent angles here must together be two right angles by proposition 13. But BGH and GHD, these two angles over here, are also equal to two right angles. He concludes from this that the angles AGH and BHD are equal to the angles BGH and GHD. So he's saying that this angle and this angle together are equal to this angle and this angle together. Why is that? Well, because they're both two right angles. They're both together two right angles, and hence must be equal to each other. Then he says, from those pairs, we're going to let the angle BGH, so we're going to simply remove BGH from those two. And what are the remainders? Therefore, the remaining angle, AGH, is equal to the remaining angle, GHD. So we simply removed away BGH, and from equals, if we remove equals, then this will generate equals. Hence, we have the equality of these alternate angles, And again, we use proposition number 27. Therefore, AB is parallel to CD. And similar to proposition 27, the previous one, this proposition neither explicitly uses the fifth postulate, the parallel postulate, nor does it depend upon another proposition which uses the fifth postulate. So this proposition, just like the previous, is independent of the parallel postulate. So its negation has no bearing upon this proposition or the previous.